So next up, want to start talking about acyl substitution, which is a huge family of reactions. There are many, many, many reactions here, but if we can just organize our study of acyl substitution in such a way that we recognize its the features that are common to most acyl substitutions. Acyl substitution. Okay, so this is what you're looking for. You're looking for a carbonyl carbon that is bonded. Look for a carbonyl carbon that is bonded to something that is not carbon and not hydrogen. I'm going to call that Z. So Z is not carbon and not hydrogen. So if you have carbon on the left and carbon and hydrogen on the right, now we're talking about an aldehyde or a ketone. Aldehydes and ketones don't do acyl substitution. Acyl substitution is a reaction of compounds that have where the carbonyl carbon is bonded to something that is not carbon and not hydrogen. So that Z group can't be more carbon, it can't be hydrogen. So what could it be? It could be oxygen, it could be nitrogen, it could be halogen, it could be sulfur, it could be a lot of stuff, just not more carbon and hydrogen. Okay, specific examples would be, here's a carbonyl carbon that is bonded to Cl. Okay, so this is a kind of molecule that undergoes acyl substitution. Okay, more concrete examples. Maybe there's a carbonyl carbon and he's bonded to oxygen. Right, that's an ester. That's another kind of molecule that can undergo acyl substitution. All right, what about a carbonyl carbon there, where the carbonyl carbon is bonded to oxygen? We get a molecule such as this. Well, that would undergo acyl substitution because I see a carbonyl carbon that's bonded to something that's not carbon and not hydrogen. That's called an anhydride. All right, another concrete example of a molecule that undergoes acyl substitution could be an amide. Once again, there's a carbonyl carbon that's bonded to something that is not carbon and not hydrogen. Collectively, all of these guys are called acyl derivatives. And what's an acyl derivative? Once again, and this is something you're going to hear me say a bazillion times, it's a carbonyl carbon that is bonded to something that is not carbon and not hydrogen. And so now this is going to be a crisis for you because we've just finished studying reactions of aldehydes and ketones, but aldehydes and ketones are not acyl derivatives. So that as we continue our study of organic chemistry, you have to make sure that you are not using an aldehyde or ketone reaction when you're working with an acyl derivative, right? So this is a very, very common mistake that people make. All right, and I'll have more to say about this very common misconception later. Okay, so now we know what is going to undergo acyl substitution. You're looking for a carbonyl carbon that is bonded to something that is not carbon and not hydrogen. Okay, acyl substitution can happen under acidic conditions, under neutral conditions, and under basic conditions. So let's look at the overall reaction in acid. There's our acyl derivative, right? And remember this Z, this is just what I'm saying is the thing that is not carbon and not hydrogen, right? This Z group, that's the thing that's not carbon and not hydrogen. This is the electrophile. It's going to be attacked by nucleophiles. that's the electrophile. We could write a resonance structure in which the attack by the nucleophile is maybe a little bit easier to see. We see that that acyl carbonyl has a partial positive charge on it because of this resonance structure. So nucleophiles are going to attack this acyl carbonyl. Under acidic, so that's the electrophile. Now we need the nucleophile. Under acidic conditions, the nucleophile is nearly always going to have a proton on its nucleophilic atom. So I'm going to represent that in this way, H-nuc, right? So that's the nucleophilic atom of the nucleophile. Okay, and so what is going to happen overall, right? I'm not talking about mechanism right now. I'm talking about the overall reaction. What happens in acyl substitution is that this thing that is not carbon and not hydrogen breaks off. The nucleophile takes its place, and then there is in the mechanism, which we will see later, there's a proton transfer. Anyway, the final product here is that thing that is not carbon and not hydrogen, that has gone away, and its place has been taken by the nucleophile. The Z group effectively functions as a leaving group, but it is going at the end of the reaction, it is displaced with that extra proton that the nucleophile came in with. So that's the overall reaction for acyl substitution under acidic conditions. The thing that's not carbon and not hydrogen goes away. Its place is taken by the nucleophile minus the proton that the nucleophile came in with under acidic conditions. In a formal sense, this proton ends up over here with the leaving group. But if this is Fred, if this proton is Fred, this is not Fred over here, right? This is Mary, this is somebody else. Let's look at a concrete example. All right, so here's an acyl derivative. There's a carbonyl carbon that is bonded to something that is not carbon and not hydrogen. Now here's the nucleophile, water. The nucleophilic atom in water is the oxygen atom. The nucleophile is coming in with a proton in a state of protonation. We're talking about acidic conditions. And so what happens is the thing that's not carbon and not hydrogen, that goes away. Its place is taken by the nucleophile minus the proton that the nucleophile rode into town with. So the products of this reaction would be a carboxylic acid and, carboxylic acid plus the remnant of this leaving group plus an extra proton. Okay, so that's an example of acyl substitution under acidic conditions. All right, so let's try another one. What about something like this? What if we had an amide plus water, acidic conditions? What would the products be? The thing that's not carbon and not hydrogen goes away. Its place is taken by the nucleophile minus the proton that the nucleophile rode into town with. So we would get something that looks like that. Okay, so that's acyl overall reaction, acyl substitution, acidic conditions. All right, so we only have time to talk about the overall reaction in base, and next time we'll continue talking about acyl substitution. Okay, under basic conditions, once again, we have the acyl derivative. The the thing that's not carbon and not hydrogen, and that's the electrophile. And now the nucleophile, under basic conditions, is nearly always going to be negatively charged. So instead of H-nuc under basic conditions, what we're really looking for is nuc minus. Very same thing happens. The thing that's not carbon and not hydrogen is going to go away. The nucleophile is going to take its place. There are no protons available, so that Z group is exiting with a negative charge on it, right? So again, the thing that's not carbon and not hydrogen breaks off. The nucleophile takes its place. Okay, one of the things that makes acyl substitution under basic conditions more complicated than acyl substitution under acidic conditions is that many, many times this guy may continue to react, but it's not going to be another acyl substitution. It's going to be some other kind of reaction, and it's frequently very challenging to identify what that second reaction is going to be. Okay, so just to finish up, let's look at a concrete example. Here's the acyl derivative. I see a carbonyl carbon that is bonded to something that is not carbon and not hydrogen. And this is basic conditions, so I'm going to use hydroxide as the nucleophile. What happens here is the thing that's not carbon and not hydrogen goes away, and its place is taken by the nucleophile. And this Z group, this leaving group, went away, but following this model here, it's going to emerge with a negative charge. The reaction is over. I mean, the acyl substitution is over, but the reaction is not over, because that's a carboxylic acid. This is an oxygen atom with a negative charge, and you know that anytime we see an oxygen atom with a negative charge, that's going to be a base. This is a base, this is an acid. The acyl substitution is over, but the reaction is not over, because frequently when we have acyl substitution under basic conditions, the product of the acyl substitution may continue to react, and that's exactly what it does here. There's the acid, there's the base. These guys are going to engage in an acid-base reaction. It's not an acyl substitution, it's an acid-base reaction, and the final products would be the carboxylate and methanol. So this is what I'm talking about with acyl substitution under basic conditions. You get the acyl substitution, but under basic conditions, the product of the acyl substitution frequently goes on to react. Okay, so I have to stop now because it's time to move on to my next virtual class, and so I will see you down the road. Until then.